So when converting from Cartesian coordinates to polar coordinates when doing double integrals, this dx dy part is what we're integrating with respect to. We're integrating with respect to x and y. But when we're converting that into polar form, dx dy is actually equal to r times dr d theta. So when we're converting it to polar form, there's this extra r here. So let's find out why there's extra r when converting. So let's think about what dx dy really is. So let's take a look at some diagrams here to visualize what's happening. So when we're talking about dx dy, what that's kind of referring to is if we have a tiny change in our x value, tiny change in our y value, and we multiply these infinitesimally small changes together, right, these little like distances, I guess we can say, then you're going to get a change in area. So when we change x by a little, y by a little, we're going to get a little change in area. All right, that's dA right here, because this is just length times width, right, gives you the area. So we want to do this in polar coordinates, right? We want to change r by a little bit. We want to change our angle by a little bit, right, in polar coordinates. And we want to see what's the resulting change in area. So you can see from this diagram here that this is my original point, right? It has this radius r, this angle theta. I'm going to increase the distance from the origin, this dr right over here. So this is my little change in distance here. And I'm also going to change the angle a little bit here. So notice how the distance goes from here to this point, right? We're going from this point originally to this point now. And notice how, once again, it forms a change in area. So this is this dA right over here that we want to calculate, right? It's similar to this dA right over here, right? Where tiny changes lead to tiny changes in area. We want to see how these tiny changes lead to this tiny change in area here. So how do we do this? Well, I know that this is kind of like length times width, right? This is the length and this is the width. And if we just multiply these two values together, we can get the change in area. So what's this length right over here? This length is just going to be dr, right? That if you just increase the radius, then the change in radius is going to be this dr here. Now what about this distance? What about this change caused by the angle? Well, if you recall, in a way, you're kind of sweeping across. This is like a circle, right? If we have radius here and then we go all around like in a circle, right? You can see that we're going around the circle. We're changing the angle. If you want to find out this length right over here, which is essentially the arc length from the circle, then what you do is you take the radius and you multiply it by that change in angle, right? So essentially it's the radius multiplied by that tiny change in the angle. And now we have the ingredients for our change in area. We just have to multiply these two values together. So dA, I'll just keep this consistent, dA is going to be equal to r d theta, which is the length, multiplied by the width, dr. Or if we want to rearrange it so that all the r's are together and all the theta is together, then r dr d theta is equal to dA. Now, one question that you might be having is, well, Ryan, if this is representing d theta, a tiny change in the angle, if I change my angle, right, and I'm trying to find this change in area, this area right over here isn't a rectangle, right? Like this is not a rectangle because when you're changing the angle, you're curving this path here. So you can't just do length times width like this, right? This isn't accurate. Well, my answer to that is, well, this is purely the diagram purpose. Or this is purely because of the diagram. All right, imagine d theta as being extremely, extremely small. So instead of this brown arrow going here, imagine if it was like right next to the point here. So d theta was so small. D theta is extremely, extremely small in this case, right? And you can see that as a result, my change in area. So you just erase this real quick. You can see that when d theta is extremely, extremely small, it looks more and more like a rectangle, right? When d theta is extremely small, it will look more like a rectangle because that change in angle produces less of that curve, right? So when we're talking about infinitesimally small things, right, we're able to get away with things like that.